Welcome to 10 minutes CS. 432 all O1 data structure. We need to design a data structure to store the strings count with the ability to return the strings with minimum and maximum count. We have to implement these functions. The first one is all1, which initializes our data structure. The other is increment key, which increments the count of the string by 1. If it does not exist, then it inserts it with count 1. For decrementing, it decrements the count to 1. If count becomes 0, then we just remove it from our data structure, and it is guaranteed that the key exists. And get maximum returns one of the keys with maximum count. So let's say there are multiple keys which has the maximum count, then we can return any of these. If no element exists, then we have to return the empty string. Similarly, for minimum key, we have to return the minimum count. And one thing to note here is we have to implement all these functions in big O of 1 average time complexity. Now let's think of it a bit. Here we can see that we have key, and corresponding to it we have count, which will be the frequency of that key. So for these sort of relations, we usually have map. So in map we can have a key and we have corresponding frequency map to it. And here we have to return the maximum and minimum. So that means that these keys should be in sorted order. So with the map and sorted map, we can think of a tree map, right? But tree map, will it be able to give us the maximum and minimum key both in O of 1? No, we can get only either of these, and the other one will have very high complexity, because tree map stores it in a sorted way, but if we have, either we can implement it as minimum tree map or maximum key map. Both are not possible. So what we can do here is we definitely need a map, but with the map to store the keys in a sorted way such that we can access, let's say it's sorted in ascending order, to access the front and the back both, that is the minimum and the maximum both, we can have a doubly linked list. Why doubly linked list? Because that will have a head and tail. With head we can get the minimum, and with tail we can get the maximum. So now here we need a map and a doubly linked list. Now let's try to implement our functions. To initialize our data structure, we need a map which will be storing the string as the key, and for value it will store the node, which is address of the node, in our doubly linked list. For our linked list we have head and tail. So we have a dummy head and dummy tail node, and these head and tail will have value -1, -1, and it will be initialized such that head next is tail and tail's previous is head. And how we are defining our node will store the frequency, that is the count, and previous and next nodes, and set of string, that will store the set of all those keys which have frequency equal to the frequency value of that node. Now let's look at our increment function. We get the key as the input. Now there could be two cases where the key is already there in map, that means that it was added earlier, while the other case is when the key is not present in the map. Let's look at the case when the key is not present in the map, that is the else case. So if that is so, then our head might be pointing to the next node which could be a tail or maybe a node for which frequency is greater than 1. But if a node is newly added, its frequency should be equal to 1. That means here we need to add a new node in our linked list. So for that we have our if condition. If the head dot next is tail or its frequency is greater than 1, that means we need to add a new node. So we create a new node with the frequency 1, and in its set we add our key, and we add our key and new node to our map. Let's make it newly here itself, head, and this is our head next, which could be a tail or any other node. So we have these pointers as this. Now we have created our new node. So our new nodes previous is pointing to head, and our new nodes next, that is this one, will be pointing to our head next, that is this node. Now our heads next, that is this node, previous, that is this pointer, will be removed from here and it will be pointing to our new node. Similarly, our head next will be removed and it will be pointing to our new node. Now if our head next initially is have the frequency as 1, then in that case we just need to add to that. Let's say this is head and this is the head dot next node, and it has the frequency 1, that is a new node will be added to this. So we just add it to its set, we just add our key to its set and we add it to our map. Now let's look at the case when our key is already present in the map. So if that is the case, then we get our current node. So our key must be pointing to our node, that we take it as current, and we check if, let's see, this is our current node and this will be our next node. So we check if our next node frequency is, if it's not equal to current frequency plus 1, so this needs to be incremented to frequency plus 1, but this node is not frequency plus 1, or if it's tail, in that case we need to create another new node and we have to make similar pointers to it. So we create a new node with our current frequency plus 1, we add our key to our new node set, we point the pointers accordingly, and then we remove the key from current set. So we remove the key from here, as we have added it here, our key has moved from current to the next one and we add it to the map. And if the next has the frequency, that is this case, our else case, when our current next frequency is equal to our current frequency plus 1, so we simply just add our key to this next node's set and we remove it from our current set and we add it to our map. Now in any case, while adding or while removing it from the current set, our current set becomes empty. That means this node doesn't contain any key, so we just remove the node. Let's look at the code for our remove node function. So in our remove node, we have a node that needs to be removed. So there will be some previous node and next node, and this is the node that needs to be removed, and it has pointers such as this. So our previous node will be nodes previous and our next node will be nodes next, that is this one and this one. So our previous nodes next, that is removed from here, and it then points to our next node, and this pointer, it gets removed from here and it points to this one. And finally our garbage collector will collect this node and will delete it. So finally these pointers will be pointing to each other. Now let's look at the code for our decrement function. So as said, if the key is not present, so we just simply return, but this case won't be there, as in description they have said that we are not calling the decrement function if you see here that it is guaranteed that the key exists in the data structure before decrementing. So now we get the key from our map and then we remove it from that node. And if the current frequency is 1, that is, let's say we have our current node and its frequency is 1, that means it gets reduced to 0. So if it's reduced to 0, we have to remove it from our data structure. So we just removed it from our map. And if that's not the case, then we have to decrement the frequency by 1 value. So there could be 2 cases in that case also. When the previous node, let's say this is the current node and its frequency is f, and this is the previous node. So if one case will be either it is equal to f minus 1, or the other case is it's not equal to f minus 1, or it's ahead. In this case we have to create a new node and make the pointers like this. So that is this case. So we create a new node with our current frequency -1, we add our key to the new node set, and we update the pointers, we remove it from our current set and we add it to our map. And for this case, when we already have a node with frequency -1, then we just simply add our node to this set, remove it from the current set, add it to the map. Now in any case, while doing such operation, our current set value, current set becomes empty, so we just have to remove this node from our data structure. So we run again our remove node current function. To get the minimum key, we already have our data structure, such as we have head, then few nodes, then we have tail. So in that case, we know that this doubly linked list we have maintained in ascending order. So the node just next to the head will have the minimum frequency. So we check if our head.next is not equal to tail, that means we have a valid node in between. So we just get any of the keys from our set. So head next will be this node, and we get any of the keys from that set using the iterator. Else, if our head.next is equal to tail, that is we don't have any valid node, so we just return empty list. Similarly, we can get the maximum key as the next previous node to our tail. So we get tail.previous, and we get any key from our set. If our tail.previous is head, that is we don't have any node in our doubly linked list, we just return an empty set. Now let's try to run submit this. Yeah, it indeed got submitted. And for all of these functions, getMin, we are just fetching the node values. So this is O of 1 and this is also O of 1. For our decrement function, here also we were adding the node or fetching the node or updating the node based on few conditions. So that is also O of 1. Similarly, for our increment function, that will also be O of 1. Thank you for watching.